Hello and welcome to Stars, Cells, and God, the show where we discuss new discoveries taking place at the frontiers of science that have theological and philosophical implications, as well as new discoveries that point to the reality of God's existence. My name is Hugh. I'm joined by my colleague here, Jeff Zweerink, and today we're going to be exploring the topic of the gambler's fallacy, new application of the gambler's fallacy. I'll be talking about the core of Mars and the core of Earth. But before we get into this discussion, I wanted to encourage you to subscribe to our channel, our Reasons to Believe YouTube channel, so that you can be notified of our new weekly videos. Learn more at reasons.org or by following us on social media at RTB_official. So Jeff, tell us about this new application of the gambler's fallacy. I had no idea you were a gambler.
I'm not well, I guess everybody's a gambler at some level, but I don't generally put money on it. But what I've found interesting in this is it's a discussion of whether the evidence we see for the fine-tuning in our universe is that evidence for a multiverse or not. And part of what I just find interesting in this discussion is that if you go back 20, 30 years ago, just kind of when I was starting getting into science, I remember reading books by, I think one by Joseph Silk, one Frank Tipler wrote a book on, kind of the early parts of the universe. And one of the dominant themes that came out of all of those books was the idea that as we probed earlier into the universe, that there are these parameters that we just have to put into our models at this point. The charge on an electron. There's nothing that determines that. But yet, once we put it in, with a relatively small number of parameters, we get this huge explanatory success of the standard model of particle physics. And the idea was very prevalent and prominent through all of those books I was reading is that when we get that final grand unified theory of everything, and I'm intentionally being ambiguous in the terms there because I think it was just largely looking at the theory of, or the grand unified theory at the time, whereas now we got this theory of everything, which incorporates, the fundamental interactions, gravity, electromagnetism, strong and weak nuclear forces, that when we finally got that, there was going to be something in the mathematics of all that that said, this is the only way, or that it specified all of those values. And so that there was nothing really left to put in externally, that it was just internally consistent.
So going from, say, 24 magic numbers that have to be fine-tuned, down to 12, down to 6. I got a book that says 6. You're saying maybe we can do it with just one number.
Well, no, not even. The idea was that there was going to be none of those that you had to specify and just put in. That the theory itself was going to specify all of that, and that this now explains everything that we see. And there's no more here. Let's put in numbers. Well, standard model particle physics has about 26 that you have to deal with. What's interesting is that as we've gone to more unified theories, when we have our looks at grand unified theories, those numbers seem to increase dramatically. And when you get to the one where you're now incorporating gravity, now you've got string theory being a model out there, and it's like, 10 to the 500 different options. And so it seems like the more unified our physics gets, the more these numbers that we have to specify are proliferating, if you will. And so really what I want to do is just contrast that picture now with the idea that is very prominent now. I think as much as that idea that we're going to find this simple or this single unitary explanation that explains everything, one of the dominant models, I would argue probably the dominant model out there today, is that we live in a multiverse, and that the reason why everything is the way it is largely because everything in the multiverse happens, and we just happen to live in this region where everything looks the way it does.
Jeff, you're referring to the multiverse model, where there's an infinite number of universes, where they're all distinct from every other universe. Is that correct?
Well, it's the multiverse of necessity in this model has enough variation to explain so that our rareness or unusualness is just part of the distribution that's out there.
Well, Jeff, maybe even before, I think it was 1983. You were probably born by then.
A little bit.
A little bit. But I remember speaking in 83 and saying that the fine-tuning is going to reach a level where you're going to see people who are reacting to God being responsible for it. They're going to say, there's this But they didn't call it a multiverse back then. They just said there's going to be this extremely large number, probably infinite number of universes where they're all different from one another. That's going to explain the fine-tuning. And, here we are in the 21st century. That's exactly what's happened.
Mm-hmm. No, and it really has. And to me, it's just remarkable, the shift in perspective, because you almost couldn't pick two more disparate ways of looking at creation. One is the creation is going to be internally consistent, everything's coherent and well-defined. And now you've got this other picture where everything is explained ultimately because everything happened somewhere. Now, and if I could remember, or if I could point out that I remember back when I was first starting to investigate the multiverse, and this would have been 18 years ago, you made a couple of comments. One comment was, you said that all multiverse models could be recast in terms of a universe model. But one of the things you did say is that appealing to a multiverse is committing this thing called the inverse gambler's fallacy. And that, the paper I'm talking about is just kind of here 20 years later, where it's kind of fleshing out and saying, are we still doing that?
Somebody wrote a paper on this?
Oh, there's a rich history of this. This is not just a paper. It's like there are people who've been addressing this for a long time. And to get an idea of what it is, you got to consider what the gambler's fallacy is. And the typical way it's illustrated is you imagine a gambler's been at the table all night, throwing dice, whatever game they're playing, and it's just like they throw the dice, nope, they don't win. No, throw the dice, nope, they don't win. Throw the dice, nope, they don't win. And if that goes on long enough, the gambler begins to think, well, I can't have a string of luck that bad. Surely the dice are about to turn in my favor. And the fallacy that's committed there is just saying, okay, this is a really rare occurrence. That means that the next thing that happened is going to fall within the normal, and I'm going to win. And what it misses is that once you throw the dice, what happens on the next roll of the dice is entirely independent of what happened on the previous rolls of the dice. So you could have been throwing a million rolls of the dice, gotten ones every time, and assuming the dice aren't stacked, the next time you roll, getting ones is not more probable. It's the probability of getting the dice are determined by the dice themselves, not any other previous rolls. Now, the inverse gambler's fallacy is a little bit different than that. There, the inverse gambler's fallacy is the guy walks in, or gambler walks in, sits down, and just throws this string of incredibly beneficial win every time sets of dice. And their thinking was, oh, the fact that I've done that means that there must be a whole bunch of people out there doing that. And so my unusual situation just falls into the distribution. I happen to be the one who got lucky, but there's a whole bunch of this going on out there.
A whole bunch of unlucky people out there.
Exactly.
Yeah.
And so that's the question that is being addressed, is positing a multiverse to explain the unusual looking nature of our universe to support life. Is it committing the gambler's fallacy? And, you spend well, maybe not a lifetime, but a lot of my lifetime at least, articulating not kind of various types of fine-tuning. There's do we live around the right kind of planet in the right kind of galaxy around the right kind of star type scenario. And I'm going to call that environmental fine-tuning, because we know that those things can be different. We know that there are other galaxies. We know there are other stars. We now know there are other planets. But there's another kind of fine-tuning, which is a little bit different in that it relates to what is the mass of the electron? What is the size or the value of the mass of the Higgs boson? How fast is the universe expanding? These are all parameters which are kind of set, if you will. There's no, it could be different, or there's no evidence we have that it could be different. All we can do is we can do our calculations and say, if it were a little different, then at least life as we know it would be impossible. It wouldn't exist, because there wouldn't be stars, the universe would expand too rapidly, whatever the outcome is. And there's a whole, again, a pretty large catalog of those related to the strengths of the fundamental forces related to each other.
Yeah.
Lots of different ones of these that play out. And the multiverse is sort of getting, it in some sense gets at the environmental fine-tuning, but that kind of makes sense in a lot of sense because, like I said, we see a lot of other of those. But the question is, when we do that with the multiverse for the fundamental fine-tuning, these things that are like the speed of light, it's just set in the universe, are we committing the inverse gambler's fallacy there? And so this paper, it's by a guy named Simon Friedrich. It says, reconsidering the inverse gambler's fallacy charge against the fine-tuning argument for the multiverse. And he just talks a lot about what is the gambler's fallacy? What is the inverse gambler's fallacy? Are we committing that when we appeal to a multiverse? Because one of the things that I have seen is that not only are people saying, well, because of all this fine-tuning, there must be a multiverse. They're actually saying the fine-tuning means that there's a multiverse out there. And you could see the connection with the inverse gambler's fallacy.
Sure.
Because that's saying, okay, they're acknowledging all of the unusual nature of our universe for life. And they're saying, okay, that now provides evidence in support of a multiverse.
There's got to be all these unlucky options out there.
Yeah.
Yeah.
And so the one of the things the paper does is you kind of have three options to explain that. One, there's a designer. Two, the laws of physics mandate it. Or three, you've got a multiverse. The kind of the three explanations that play in there. And if I were to characterize that when I was first getting into physics, the laws of physics were what explained all of this, that we're going to find an explanation that says all of this has to happen this way. I have always argued, and you have always argued, that this is evidence pointing towards a God who's created the universe and fashioned it for a purpose. But this multiverse idea really seems to be kind of where a lot of the scientific community resides at this point. And I will say, in my opinion, whether there's a multiverse and whether there's a God or not, it's either the multiverse or a God. They're really two separate questions, because if I were to give my position right now, I think we live in a multiverse that God created, and I think that's what the evidence says. I think you and I may differ a little bit on that, or there's some subtle points there, but just because there's a multiverse doesn't mean God doesn't exist.
Yeah, and there's very different versions of the multiverse. There's a Christian version, there's the atheist version, there's a deistic version. So it's not just one multiverse theory out there.
Exactly, no, and I think that's an important thing to say, because it tends to get washed up as, oh, the multiverse explains everything, and really you have to kind of question what's going on. And part of what I think is interesting about this is that there's, kind of just addressing, and this is a philosophical paper, and so they're kind of wrestling with, are we doing our argumentation and reasoning well? And so they're trying to look for other places where we reason similarly, where it's an analogous way of reasoning, and then asking, is that committing the inverse gambler's fallacy? And one of the places where they do that is they say, all right, we know Earth looks incredibly well designed to support life. It's got the right size, right atmosphere, right distance from the star, right kind of sun, those sorts of things. And they say, one of the ways of explaining that is saying there's a large number of stars where there are planets orbiting that don't have all of the conditions required for life. And so, yes, ours looks unusual, but in the large distribution, we're now no longer unusual. That's very similar to this reasoning to the multiverse in that sense, that is saying, okay, well, everything's in our universe the conditions for life in our universe seem extreme and constrained. The way to explain that is that there are a lot of universes out there where that doesn't happen. We happen to be in the one where it does, because the one thing we do have to take into account in all of that is that our existence necessitates that we see something consistent with our existence. So on all of those planets where we could not be on those planets where they're too close to the star and it's too hot, or there's no atmosphere, or because we have to be in conditions that are suitable to our existence. But when it comes to looking at that environmental fine-tuning, we're not committing the inverse gambler's fallacy, because we actually have independent lines of evidence supporting that there are these other planets around other stars that have different conditions. So it's not just saying, well, there's got to be all of these planets in order to explain this. We actually have independent evidence that all of these other planets actually exist. Now, we can quibble over whether there are enough of them and what are the constraints, but we're not committing an inverse gambler's fallacy by just saying, okay, we could explain our unusual nature by arguing that we're one amongst this large ensemble of planets that are out there. Now, the question comes, are we doing that when it comes to the multiverse? And again, you got to remember that what happens on Earth is unrelated to what happens around planets around any of these other stars. So it's not like, well, there's just enough of them out there, you're bound to get one. Same sort of thing happens in the multiverse. You know, just because there may be all these vast other multiverses doesn't mean that what goes on there doesn't impact what goes on here. So it's not like there's some sort of tie where, oh, because we're here, there's got to be multiverses out there because we're measuring the consequences here. It does really seem like we're arguing we're unusual. In order to do that or to make that seem normal, there's got to be this large ensemble. Now, I think one place we may disagree is I actually think there may be independent evidence for the existence of a multiverse. And where I would say that is our best explanation for our universe is that we have this inflationary epoch. And one of the things inflation does is that it takes very small regions of space and expands them out to enormous regions of space. And so, you know, I like Max Tegmark's description of the multiverse, that there are 4 different levels. There's just a whole lot more of the same stuff out there. 2 is that there are other bubbles where the physics may be different. 3 is kind of a quantum mechanical multiverse. And 4 is a mathematical multiverse. And really, from a scientific perspective, we're dealing with the whole lot more of the same stuff, the other bubbles, and the quantum mechanical one. But to me, if inflation happened, we live in that level 1 multiverse. What inflation's doing actually means there's a whole lot more space than what we can see.
A lot more space-time bubbles out there.
Well, whether there's other bubbles or not is independent. It just takes whatever our region is actually much larger than what we can see. And so there's a whole lot more space out there that we will never be able to see.
Right.
And so I find that a very non-controversial idea that we live in that kind of multiverse.
Well, especially when you recognize that the inflation has to be fine-tuned for life to exist in the universe.
Well, that's a different question too.
Yeah, we have to live in an inflationary.
So, but I mean, there's experimental evidence that we live in an inflationary universe. It's not conclusive, but that's where the bulk of the evidence is pointing. And so there's not a lot of controversy in that. We live in this level 1 multiverse. So the way I say it, if inflation happened, we live in a level 1 multiverse. Now, the mechanism of inflation is typically there's this false vacuum that inflates, it decays. You know, how that all plays out is a little bit different. But the mechanism of inflation that makes our universe is going to make a bunch of other ones too. So I think the way I say it is, if inflation happened, we live in a level 1 multiverse. If our mechanisms for inflation are correct, we live in a level 2 multiverse. And so to the extent we can ascertain whether inflation happened in our universe and understand it, I think that provides evidence that we do live in a multiverse, whether level 1 or level 2. I actually, if you go back to making me put money on it, I would bet that we live in a level 2 multiverse. And so in that sense, I don't think the multiverse, or appealing to the multiverse, is committing the inverse gambler's fallacy strictly in that sense. Where I do think it's running into problems is that the assumption is that all of these other multiverses explain what we see.
Right.
I think we can say that a multiverse exists, but we have no idea what it actually looks like. It may look exactly the same way as ours does. In that instance, then, the multiverse doesn't explain why our universe looks so suitable to life. To get the multiverse to explain that, you have to have this great diversity of where speed of light might be different, the weak nuclear force doesn't. You have to have that range of conditions actually exist somewhere out there in order to explain that. And the problem is, I think we can establish that a multiverse does exist. I am not sure that we could ever explain or actually observe or provide any evidence that the stuff that we need to vary actually varies out there. And so in some sense, the multiverse is not committing the inverse gambler's fallacy and that it probably exists. In another sense, it is committing the inverse gambler's fallacy because we're assuming the distribution out there that makes ours unusual.
Or assuming the characteristics of stuff we can't see.
Exactly. And we're never, probably not in my lifetime will we ever be able to weigh in scientifically on whether that's true. And there are some discussions of how do we go about, if we live in a multiverse and everything happens, how would we be able to measure that here? I think there's an interesting side consequence of that if we're going to do it or go by that kind of multiverse, science may ultimately end up just being bookkeeping of figuring out what are the relevant or what are the possibilities that are out there and where do we fit into all the possibilities, rather than science saying, oh, this explanation is actually better than that explanation. Because as long as that explanation is consistent, it happens somewhere in the multiverse. How do we know whether we're there or whether we're in a more unusual situation? We have no way of determining that. So I think if we're not careful, if we're using the multiverse to explain the uniqueness of our universe and our Earth to support life, we may end up undermining the very fabric of science itself. And I think we need to be really careful how we proceed there.
And this is what this gentleman wrote in the paper?
That's not what he's writing. That's one of my conclusions of looking out of that. Because if you're now starting to ask the question, how do you do predictions? How do you do science in light of a multiverse? It now becomes a statistical question, because you can't actually go out and measure to see whether that was correct or not. You can draw statistical probability inferences. And we do that in science all the time, but there's this underlying philosophy or recognition we have is that very often the simplest explanation is the one that's right. If we're positing that everything that can happen does happen, the simplest explanation is no longer, we have no reason to believe the simplest explanation is the correct explanation here, because we have no way to verify that anymore.
Right.
And so we need to be careful what we do. I have this suspicion that the longer we go down using the multiverse to explain rare circumstances, like why is our universe the way it is, if we continue to do that, we're going to undermine the fabric or the philosophical underpinnings that allow science to work so well. And it will become kind of what sort of things can we make, and statistically speaking, what are the possibilities out there? Because we'll have no way to determine, well, this possibility could explain how we are. This possibility could explain, how do you distinguish between those? There's no experimental evidence you can bring that would weigh in on that.
Here's one place where I think we can make progress. I mean, we already know that inflation is crucial to have life, and we got very strong observational evidence that we live in an inflationary universe. What we don't have right now is what kind of inflationary universe we live in. What is the precise inflationary model? However, I think there's possibility that astronomers can actually relatively soon, maybe within a decade, identify what kind of inflation is happening. And what would be interesting, does that specific kind also need to be fine-tuned to explain life in the universe? So that's something I'm looking forward to.
Well, I think there's a lot of evidence that even supports that what happens in inflation requires fine-tuning. I mean, it's kind of talked as inflation just kind of wipes everything out. It provides a blank slate. It does all of this. And in some sense, it does. But when you look at what sort of potential space needs to be in to cause inflation, it's a highly constrained environment.
Right.
In fact, there are, I think the fellow's name was Paul Steinhardt. Originally, he was looking at inflation because it seemed like it explained away the fine-tuning. And then I think he's on record as saying, you look at what goes on in inflation and the fine-tuning just gets put into, instead of, it may explain this, but you end up with this other set of fine-tuning to make inflation work, because getting an inflation potential is not a trivial thing. So I think even if inflation worked, that doesn't explain away all the fine-tuning.
Yeah, I think that's an interesting point, is that people have appealed to inflation to try to get around the fine-tuning argument, but they're discovering they have to fine-tune the inflation event to explain life. And maybe there's even more fine-tuning there that we've not yet recognized.
Well, it just certainly, as you're saying, it adds to the weight of evidence that what we see in our universe is unusual. It seems atypical. It's like, if you just ask, what do you expect? This isn't what we would expect. Even when you throw in that we're here to see it, it seems better than what we need, if you will, or better than what you need for life. And so I think we'll continue to find that. largely because I think God has created the universe and he's done that for us. And that's part of the fascination, that he has given us the desire to understand things. And as we grow in our understanding, we find more stuff like that.
Well,
but even to your point, you made a point that let's say we can figure out what kind of inflation it is. That still doesn't answer the question. So we know what kind of inflation it is. Does that actually mean that the speed of light changes in the different regions of space or not? We still have because all we can sample is our universe,
right,
and those are specified here, we don't have any experimental evidence that says, yes, they can actually be different. Now, I will make a slight caveat to that, in that there are measurements that indicate that maybe the fine structure constant changes over distant values based on quasar measurements of certain atomic transitions. So there may be some evidence, and we may find evidence of that in the future. But as of right now, there's no compelling evidence that any of the fundamental constants are anything but constant. And so we have no reason to think, except that we could envision them being different in our mind. We have no experimental evidence that they actually change. And so even if we find inflation and find out what kind of inflation, that doesn't mean that it has all the variety that means that our unusual values fit within this distribution.
Well, I'm also fascinated that we humans seem to be at the right time and the right place in the universe to discover that there is inflation. Inflation's not easy to see.
Yeah.
So,
no, I mean, it is. And one of the things I love about being a Christian and being a scientist is that it makes sense why we live in the creation we do, why we live in this universe, is that God has created this universe. And there's so much about human life that we don't actually need to know what's going on out in the heavens. I don't know that there's any aspect to where knowing what's going on in the heavens helps us steward the earth better, like we were given the charge in the Garden of Eden there. But it does explain why, if God has revealed himself in Scripture, God's revealed himself in creation, we're going to explore those forever and not exhaust fascinating things to learn. And so, as we're going out and exploring inflation, there may be things that we couldn't see because we're at the wrong time that we may know later. It's like there's no limit to what there is to explore because of how God has created us in his image. And it's not just a fun game that we play for a while.
What we can explore within this universe that God created for us to inhabit, but there are things that we can't explore.
Yeah.
We'll never get the mind of God.
Mm-hmm.
I mean, there's certain physicists who have made that claim. I'm going to discover everything that God knows, but hey, we have limitations. I mean, if there are other universes out there, we can't see them. The very physics of the universe means we're limited to what we can see in this universe.
Unless God chose to do things in a way that they interact with our universe in a detectable fashion. Yes. That's entirely a possibility at this point. And scientists are looking for those sorts of signatures. Haven't found them yet, but
even there are, for example, it's hard to do physics on the angelic realm.
Exactly. No, I agree.
You can't go there.
That's right. Well, and to that point, in the new creation, there's going to be new stuff we're going to be learning. Now, whether that's more fascinating than just being in the presence of God, I am a little less sure that it's going to be fascinating studying creation when you can actually be in God's presence more. But I think what there is to learn about God and his revelation will never be exhausted, even
Jeff,
in eternity.
An encouraging word for you. Scientists will not be unemployed in the new creation because we're going to be managers over the new creation, which means you're going to need to know the science of the new creation.
Fair point.
We're not going to be unemployed.
If you got the worry about, do I need to go out and do my work today, or do I get to just be in God's presence? I think being in God's presence may be more enjoyable. So.
Right. But it won't be either or.
No, I don't think it's either or. So.
All right. Anything else you want to add to this?
No, I just thought this was kind of an interesting discussion that was allowed a kind of retrospective on just how things have changed over the last 20 years, that we have gone from we're going to find the solution that explains our universe to our universe is one of just a bunch of whole mess of multiverse universes out there. And if we're not careful how we think about it, we could undermine the very fabric of how science is being done.
Yeah, and science is under threat today because a lot of scientists are moving away from the Christian roots of science. So I think those of us who are Christians, hey, this is the root of science. This is why science works. We need not abandon that.
Yeah.
Well, Jeff, I've written now 6 books on fine-tuning. I'm thinking about writing a 7th book. So I want to just share in my segment about a new fine-tuning discovery.
Okay.
And it's all about Mars. And on Mars, they've had this InSight lander. It's been in operation for 4 years. A huge Martian dust storm shut it down. But there's so much data that's been collected over those 4 years that planetary astronomers are still coming up with new discoveries based on their analysis of that 4-year stint of data, which was from about 2018 to 2022.
Okay, so it's just recently quit working then.
It just recently, it was shut down about 6 months ago.
Okay.
So there's still, and there's more discoveries that will come out of it. But what's interesting about InSight, and I got a little figure here just showing you what InSight looks like. You can see the solar panels that provides it with the energy. But the big contribution of InSight is that little thing you see in the foreground. That's a seismometer.
On the left or on the right?
On the left.
On the left, okay.
Yeah, that little hemispherical thing.
Right.
That's a seismometer, and it's the most sensitive seismometer that's ever been put on the surface of Mars. And InSight's objective was basically to determine the structure of the interior of Mars, and to do that, they needed to have a good seismometer there. And I think this next slide.
Out of curiosity, go back there for you.
Go back there? Sure.
So you've got the lander. It
Right.
comes down. What looks like a piece of tape or ribbon cable going out to this thing. How in the world did it get out there?
I don't know how it got out there. You can see it's got feet.
Maybe
So-
maybe it walks. I'm just fascinated by the technical and engineering capabilities of NASA scientists and other people involved in this, because you look at that and think, oh, that's not a hard deal, but there's nobody out there to pick that up and set it down. It's
No.
got to get there by itself, and that's not a trivial thing. So-
Well, I'm guessing that when it did land, this thing just detached from the lander, and they didn't really care where it landed. That's my guess. And you notice it's tethered. That tether is crucial because that's where all the
That's the data. You get the data into the main
yeah,
thing.
that's basically an
Well,
electronic
I'm just thinking,
stream.
okay, it detached, but it needs to land on its feet.
Right.
And that's, a foot or better away from the edge of the craft. So there's got to be some engineering that made it happen to get there, because both of them lined up very well. So
And you can see the other one's got feet as well. I'm guessing that they were underneath the thing, and as soon as it hit, instructions came from JPL,
right.
and it detached. And because there's only like a foot and a half from the bottom of the InSight to the Martian surface, good probability it would land on its feet.
Maybe, yeah.
And
Anyway, I find
Yeah.
the mechanics of that fascinating.
And
So
I'm guessing on all this, but I think it's just a random look, because it doesn't matter where it lands on the Martian surface.
no,
so-
that's fair. I would just say it looks pretty orderly and set out that way. But anyway, go ahead with your discovery. We
Okay.
could talk about that for a long time, and neither of us know the answer.
And here's a close-up here, and this is an interesting photo. This is actually taken by InSight.
A lot more dust.
Yeah, shows a lot of dust, so it's a recent one. And you can see there's a lot of dust over the seismometer now. This was taken just before, in fact, this is one of the last images taken by InSight.
Okay.
So it's just before the dust shut down the instrument. But you can see the Martian horizon there,
Right.
and there's a seismometer. And but what they noticed in analyzing the data is that several months ago, this seismometer detected 2 seismic waves. And
Okay.
one was from a Mars quake, and the other one was from a small meteorite striking. But the quake took place in the opposite side of the planet, and likewise, this meteorite struck on the opposite side of the planet. And so the seismic waves went through the core of the moon.
Yep, my recollection was they were able to determine that it was the meteor because they could record when the time hit of the quake, And then they also had images that showed that there was a meteor that showed up in between there, which, again, is pretty fascinating what they were able to figure that out.
Well, they both happened relatively close together in time, but they were far enough away that the wave actually had to go through the core of the moon.
Right.
And so this was the first opportunity. This is one of the reasons why InSight was set there. They're hoping to discover, hey, let's look at the crust, the mantle, and the core of the moon. But the Martian core is not that big.
Right.
And so they were just hoping to get seismic events. And fortunately, they did.
They got one. All right.
They got two.
Okay.
And so these two have been analyzed to determine, okay, looks like we got a new measure for the size of the core.
Okay.
A little bit bigger than what they thought it was. But we're still looking at 1,795 kilometer radius. Now that's about
1,795 kilometers. So it's about 1,000 miles.
Yeah.
For a radius.
Slightly more than 1,000 miles. And we're looking at about 53% of the diameter of Mars is the core of the moon.
That's
Mars.
what I was saying, because Earth's only 4,000
core-
mile radius. How large is our core? I don't have that number off the top
It's
of my head.
55% of the Earth's diameter. So
Earth's core is?
Earth's core is. That's included the inner and the outer,
Okay, all right.
the two together. And that's one thing they discovered with these seismic waves is that the Martian core, unlike Earth, doesn't have a solid core. It's just one big liquid core.
Okay, so it's all solid instead of having solid and liquid like the Earth does.
No, it's the other way around. It's all liquid.
It's all liquid.
It's all liquid.
Has no solid core. Okay.
Has no solid core.
All right.
Whereas Earth has a solid inner core and an outer liquid core.
Okay.
But Mars, the evidence is strongly favoring that is liquid all the way through.
Okay.
And but it's approximately the same proportion as we have on the Earth.
Okay.
But that similarity is deceiving in that Earth is a much bigger planet.
Right.
And so if you actually look at the total size of the core, Earth's core is 7.3 times bigger than the Martian core
Okay.
in terms of its volume.
In terms of its so just not looking relative to the size of the planet, just Earth's core is noticeably larger than Mars's core.
Yeah, and that's looking at Earth's liquid core is that many times bigger. It's about
Okay, so Earth's liquid core
is about that many.
Oh, okay. Are you just comparing the liquid parts of the two cores?
No, pardon me. That's 7.3 is a total size, the volume of Earth's core compared to the total volume of Mars's core.
Okay.
And our inner core is slightly smaller than the total core of Mars.
Okay.
But the other major difference is the density. And this is kind of the surprising thing, is that thanks to these two seismic waves, they were able to determine that the density of the Martian core is surprisingly low.
Okay.
Comes in, I think the number is, yes, it's about 6 grams per cubic centimeter.
Okay.
And the top of Earth's liquid core is about 9.5. The solid core is 14.5.
So Earth is much more dense, which presumably has a lot more iron in it.
Well, that also came through. Is that both cores are dominated by iron, but in Earth's case, iron and nickel account for about 95% of the total composition of our core. For Mars, it's only 80%.
Okay.
So that means that the Martian core has got a lot more light elements.
Which presumably leads to the lighter density there.
Well, that's a factor.
That's a factor.
But another factor is with Earth, you're going to have a lot more pressure.
Right.
So it's going to increase the density too.
Yeah.
And so they're trying to determine, okay, based on just these two seismic waves, what are these light elements? And they said, well, it's going to be a combination of hydrogen, oxygen, carbon, and sulfur, where sulfur is likely the dominant component.
Okay.
And in the case of the Earth, silicon is one of the light elements. So we have 5 light elements that make up the composition of that 5% in our core. In the case of Mars, it's 4.
Okay.
So silicon's missing, but you got the sulfur, the oxygen. That's the other thing too, is that it seems like in the case of Earth, carbon and oxygen are the dominant light elements, whereas in Mars it's sulfur.
Okay.
So they're getting an idea of the differences. But the paper that was written basically concludes by saying, now that we have this knowledge of the interior structure of the Martian core and its composition and its density and its pressure, this explains why the Martian magnetosphere shut down so quickly.
Okay.
So, Earth has had a magnetosphere, for the last 4.5 billion years. Mars had a magnetosphere that petered out sometime previous to 4 billion years ago. And the fact that it had all these light elements, and it's not enough just to have a liquid iron core. You got to find some way of circulating it.
Okay.
So they're basically saying this structure and composition of the Martian core explains why the circulation shut down so early.
Because?
You're going to get some circulation with the light elements at the interior diffusing upwards and causing some circulation.
Right.
But unlike the Earth, you don't get the formation of a solid core. Formation of the solid core in Earth actually generated several means of convection. Number one, you had a much bigger core under higher pressure, so it meant that you got a much greater temperature differential between, say, the bottom of the liquid core and the top of the liquid core. It's over 1,000 degrees centigrade. Think of something like 1,400 degrees centigrade. And that huge temperature differential contributes significantly to the convection.
Right.
And the fact that you had a solid core keeping those light elements, again, the pressure of the top of the Earth basically squeezes out at a very slow level these light elements from the inner core into the outer core. That also contributes to convection.
All right.
In the case of Mars, that was contributing to the convection early in its history, but it basically ran out.
Right.
So once it becomes evenly diffused within that liquid core, it doesn't contribute to convection anymore.
Okay.
So all you got left is a temperature differential, but given how small the core is, the fact that it's liquid from top to bottom, you're not going to get a big temperature differential.
Right.
So those are the two reasons why they're concluding that it shut down sometime previous to 4 billion years ago. And of course,
and we have data that shows that it shut down that long ago, correct? So it's not like we're saying, oh, this is how long it would last. We're trying to figure out why did it shut down so long ago.
we're trying to figure out why it shut down, but it's giving additional support to the analysis of Martian rocks. Because in Martian rocks, you can look at the magnetic characteristics and say, hey, this has not had a magnetosphere in a long, long time. That was our evidence for why it shut down early. This is supporting evidence, and it's actually stronger evidence than what we have with them. Because with the Martian meteorites, I think we've only got 22 that can be analyzed. So this is more compelling evidence. But what I thought was interesting is how the paper closed saying, this is something we would expect to be typical of rocky planets. Earth is exceptional. And one reason why it started with a lot more heat. And that's because the proto-Earth fused with a second rocky planet, Theia. That merger event basically shot up the interior heat of the center of the Earth, so it had more heat to start with.
Right.
It actually got more mass, so it probably got a lot more iron, explains why the core is so much bigger than the Martian core. And then the other big factor is Earth had a moon. And so the early Earth, you weren't getting, there was no solid core. It was liquid entirely. So that would give you some convection, but not strong convection. But early in Earth's history, you had the moon nearby. And its tidal forces were a significant factor and contributing to the convection.
Right.
So it explains why the early Earth had a strong magnetosphere, and the moon's spiraling away. So now it's too far away
Right.
to be a big factor. It still contributes to the convection, but it's
smaller. Yeah,
we're talking 1 or 2%.
This is kind of an interesting discovery because there's this. Again, if you look back over the last 10-ish years, we're starting to find planets around these red dwarf stars, and they seem to be much more Earth-sized. They're far more Earth-sized. You don't have the gas giants there. And one of the things that seems to be interesting that comes out of this is that we're going to find, we're finding planets that are even lighter than Earth at this point. Seems like there's this dynamic that, you've got to have a planet that's not Jupiter-sized or Saturn-sized because that's going to have these enormous atmospheres. So you need something Earth-like. But if you get too much smaller than Earth-like, you run into this problem like we're running into with Mars, where it doesn't have the necessary internal heat to drive the convection to keep the magnetic field, and it doesn't have the gravity to maintain the atmosphere as well. And so it seems like Earth has this can't be too big or can't be too small type scenario forming.
If you make the planet any bigger, it's going to have a lot more, small volatile elements around it.
Right.
But you need it to be that big to have this huge core.
Right.
So the fact that the Earth has a core that's more than 7 times bigger than Mars, that's very important to sustain a long-lasting magnetosphere. This actually shows you where the meteorite hit and where the earthquake took place. So relatively close
together. That would be a Marsquake. It cannot be an earthquake. So.
Marsquake. Thank you, Jeff. But it actually shows you how it goes through the core. And over to the left is where you got insight, picking up those waves. And but this next slide actually shows you the magnetosphere of the Earth and how it protects us from cosmic radiation and solar radiation that otherwise would kill. Might not kill the microbes, but it would certainly be a bad news for you and me.
Yeah, it does. Magnetic field's a good thing to have around the Earth.
It's a good thing to have around the Earth. And the paper basically concludes as saying, Earth, Mars is probably typical, Earth is exceptional. You got this big rocky planet, an enormous core, very high pressure, high temperature, and we got the solid core at the very time when the moon began to be too far away to be a big contributor.
Right.
That to me is one of the most amazing things. Just when the moon was no longer able to sustain a strong magnetosphere, the solid core formed, which immediately generated a second source of convection we didn't have before. And the timing to me is eerie. It happened right at the time we needed it to happen.
That is one aspect, as I've just kind of looked at how people respond to the fine-tuning evidence is, there's a part where you say, well, life's just going to adapt to the circumstances around is one of the responses that's there. But, as I've looked at Earth, this is just another example of when you look at the early Earth and where we are now and the changes that have happened. The sun has gotten much brighter. The oceans have gone from being oxygenated to not oxygenated to oxygenated. Continents have formed and cover a substantial fraction of the Earth. Life has been here in very different forms. There are numerous times where some of these changes, the atmosphere has changed dramatically, where these changes could have been catastrophic to Earth, but they happen together in a coordinated fashion so that the surface temperature of the Earth has been plus or minus 10 degrees for the last 4 billion years. And this is one example where two things are at play. One is you got the moon's magnetic field and the Earth's magnetic field, and this dramatic change happened so that there's this continuity on the Earth. It really has, to me, it has that eerie feel of somebody's orchestrating this.
Well, especially when you see precise timing happening multiple times.
Right.
I mean, I'm also fascinated by the way iron is designed. When it's under high heat and high pressure, it can form multiple, features. You get the hexagonally, crystallized iron, and you get the cubic crystallized iron. And what's interesting is that they liquefy at temperatures that are about 1,000 degrees centigrade different. And there's the eerie timing too, because you get the moon slowly spiraling away, which means its contribution to the convection of Earth's core is getting weaker and weaker as it spirals away. But first you get the hexagonal iron solidifying. Later you get the cubic iron solidifying. And so that means different parts of that iron is solidifying. But you get both.
And that's all giving off heat when it does that. So
it does, and it contributes to the convection. But it's like, isn't it eerie how you got these two different kinds of crystallized iron at very high temperatures and pressure, but they become solid at different temperatures. And becoming solid at different temperatures, it allows for the smooth transition, because the solid core started off very small, and it's getting bigger and bigger. It grows by about 1 millimeter per year.
Okay.
So it's like we see throughout the history of the Earth that these different factors that contribute to the convection of Earth's core, which is crucial for a magnetosphere. Again, multiple factors, all carefully fine-tuned, thanks to the design of iron, thanks to the design of the moon and what's happening, and the design of the Earth. But it's all crucial to have 3.8 billion years of life history in the Earth.
I agree. Pretty fascinating, Hugh.
Okay. Well, thank you for joining us today in Stars, Cells, and God. Join the discussion in the comments below. And remember to like this video and to subscribe for more content. New episodes of Stars, Cells, and God release each Wednesday and are available here on YouTube and on your favorite podcast app. Be sure to share this video with a friend, and remember, the more we know about science, the more reasons we have to believe in Jesus Christ as Creator, Lord, and Savior. Thank you.